Swayam Prabha. Digital India. Educated India.
Hello, welcome to this lecture of the course Elements of Mechanical Vibration. Let us now also look at how we can use this energy method in solving some other practical examples, and maybe before we take up another practical example, we will try to see how the effect of mass of the spring influences the natural frequency. Okay. We have been assuming that when we write the governing equation or generate the governing equation for such a simple spring mass system, we often assume that this spring is massless. Okay. So, we always say that the mass that is supported by the spring is heavy enough or much higher in terms of its inertia property compared to the mass or inertia of the spring itself. Right. So, in that situation, yes, many times the contribution from the spring mass may not be significant and the natural frequency obtained may be accurate or practically quite close to the real value. However, suppose if the springs are having significant mass, how do I account for the spring's mass in obtaining a more accurate estimate of the natural frequency? Because whatever we say, actually if the mass moves and oscillates with certain velocity, the entire spring is also moving. So, each of the elements of the spring also has some kinetic energy associated, right. So, apart from storing the potential energy or strain energy because of the stretch in the spring element, it can also store some kinetic energy. The mass which is supported by the spring, it is in comparison to the stretch in the spring, the mass is definitely is always considered rigid. So, there is no strain energy stored in the mass simply moves like a point mass. So, it makes sense to consider the kinetic energy completely focused or completely concentrated in the mass, and the springs are typically massless. But supposing if the springs are not to be considered as massless, how do I consider or include the effect of the mass of the spring? So, for that let us assume that the mass itself is having a velocity, let us say equal to v at the end of the spring here, that is of the mass itself, and you would agree that the velocity will keep dropping to the point of contact with the ground of the spring. So, the velocity of the spring is going to be 0 here, and it will be having a maximum velocity here. Similarly, that if I show the displacement, then the displacement is going to be maximum at this end of the spring, and it will be 0 here. So, we can assume a linear displacement profile, which means that if the displacement here is 1 unit, it will keep on gradually reducing. Each of these individual spring elements will have a displacement linearly related to its position from the ground, position from the fixed point. So, let us assume a small elemental length of this spring, which I will define as this spring's small elemental length dx of the spring, positioned at a distance equal to x, let us say from here, okay, and the velocity of this mass is v at its end of the spring, and we assume a linear variation of this velocity and displacement both. What will be the kinetic energy, a small elemental kinetic energy of this element dx? It will be equal to half the mass of that element dm times the velocity at that particular point. So, if I call the v at that position x as the velocity of that spring element dx, this becomes the elemental kinetic energy of the system of this particular spring element. Okay. V at this position would be different than this V. V is the maximum value or the instantaneous V at the tip at the end, and that itself is the velocity of the mass. Now, if we assume linear variation, then I can write this as half of dm. I will write as the linear mass density times dx, that basically is the mass of this small element here of the spring, and Vx I can write equal to V times x over L. L is the total length of the spring. So, this is the total length of the spring. Okay. And squared, of course. So, this element a differential kinetic this kinetic energy of this differential element is going to be now half of rho L V square x square by L square dx, and this kinetic energy of this small element will keep changing. So, if I consider this small element, the kinetic energy here will be much larger. It will be large because the velocity is changing all the way from the root towards the free end of the spring or where the mass is attached. So, if I want to know the total kinetic energy of the system, if I call this as Ke, it's we will have to integrate this dk, which for the entire length of the spring. So, which is going to be 0 to L half rho L V square x square by L square dx, and that we can show that it is equal to half rho L V square over L square x cube over 3, and of course, if you solve this you will get this as half. Now, rho L into okay, so rho L and V square L upon 3. Okay. So, rho L into L itself is what? The mass of the spring. So, half rho L into L is the mass of the spring times V square, and that is divided by 3, right. So, what we can see here, that if you consider only the spring itself has its own kinetic energy, and that kinetic energy is given by half of mass of this 1/3 the mass of the spring times the square of the velocity of the mass. So, if I now want to consider both mass as well as spring, the spring has its own stiffness, but it also has its own mass, and the mass supported by the spring is capital M, then it is quite clear that the total kinetic energy of the system, consider the kinetic energy of the mass plus that of the spring, this is going to be half M let us say x dot square, if this is x and x dot, plus the kinetic energy of the spring, if I call this as KES, is half ms over 3 x dot square, because x dot we considered as V. So, which basically tells me that if I want to now write the natural frequency of this single degree of freedom system, but considering the mass of the spring is going to be k over m plus ms over 3. Okay. You can easily show using this expression of kinetic energy and the potential energy stored in the spring. It is a straightforward to show that the natural frequency expression turns out to be this, which actually means that if I want to add or include the mass of the spring, we need to include 1/3 of its mass, and the reason why it is not full mass, because each element of the spring has a different velocity when it is oscillating, and therefore it can it so happens that the entire spring's contribution happens to be 1/3 of its mass contributing to the kinetic energy. Is that clear? So we use this expression of kinetic energy. Maybe if I also show the potential energy expression here, the spring stiffness multiplied by x square, that is your, sorry, wait a second, this is the potential energy or strain energy in the spring. So, if I write this as d dt of V plus T equals 0, it basically means that it is half Ks x square plus half m x dot square plus half mass of the spring x dot by 3 x dot square equal to 0, which if you solve you will get the governing equation as m plus 1/3 of ms, okay, x double dot plus ks into x equal to 0. That is what you will get by solving this equation, which again will mean that you will get this expression of its natural frequency, right. So, this is the second example, basically to highlight how the spring mass can influence the natural frequency value. But you must notice here that only 1/3 of the mass of the spring contributes, and usually the mass of the spring is not very significant, but if you want to have a very accurate value of the natural frequency, maybe you can include the mass of the spring. Okay, so the next example, wherein we will again implement the energy method to obtain governing equation of motion and expression for natural frequency, is the example here for a rocker arm tappet valve mechanism. So, the example here is it says that the idling speed of a 4-stroke IC engine is 550 rpm. A cam follower system is used to is used for fuel control valve, which is this, and the push rod is excited by the cam mounted on the camshaft. So, this is your camshaft, and this is the cam that rotates. We all know from our dynamics of machine, theory of machines course, how the cam shaft is connected to the main engine shaft and how it operates at half the speed of the engine, and how it operates the valve to let the fuel into the cylinder. So, this push rod is being pushed by the operation of the cam, the rotation of the cam, it sort of uses the leverage that we get here in operating the valve in the cylinder against the spring pressure. So, this is the spring, the coil spring, which is connected to the other end of this rocker arm here, and it is fixed to the cylinder head. Okay. So, the spring is fixed at its one end here, and at the other end it is just butting against the rocker arms one end. The other end, the push rod is butting here. So, the push rod pushes the rocker arm, it rocks. So, obviously, the degree of freedom that we can consider here as theta, and we are supposed to ensure or probably find the spring stiffness, so that there is 20% separation margin for engine idling speed from possible resonances. Okay. Now, we will come to this point shortly. What does that mean? But first, if this is the vibratory system that we are supposed to analyze, our first step of vibration analysis tells us to get a simplified vibratory model. Okay. This is a physical system, of course, sketched in a very simplified way, but still it captures its motion characteristic. So, this rocker arm has some mass, and its mass moment of inertia is given. So, if I want to now treat this as a vibratory system, what I can definitely say is this lever, which is fulcrumed here, is the main inertia of the system. Of course, this push rod can be treated like a spring. The push rod is long enough, it is flexible. So, you already have the spring stiffness given of the push rod. So, not all the time you should not all the time all the structural elements will show up like a coiled spring. So, this rod, which could be a circular one, if it is slender one, it will have its own longitudinal stiffness. So, this itself can be modeled like a spring, but it is not a normal spring. We just saw how the spring's own mass can influence the natural frequency. So, by giving the mass of the push rod, we can, if we want to, consider the mass of the spring in the analysis. At the other end, what is happening is that this valve is connected to this end of the rocker arm. So, there is a valve which is like a cylindrical piece with a flat valve at the tip, but as the rocker arm moves in the angular direction with angle theta, the valve simply gets pushed up and down. So, whatever is the vertical speed this rocker arm end has, let us say if I call this as V, the same velocity will be that of the valve. The valve has been given with a mass 0.25 kgs. So, it in a way kinematically it can be treated like a lump mass itself attached to the end of this rocker arm. So, this valve, the velocity of this valve, for the sake of considering its contribution to the kinetic energy of the system, we can as well consider the valve mass to be situated here, because the velocities, whether you consider it here or here, is going to be identical, except of course, if the valve itself deflects. Now, if it deflects, then it is not the case, but we have been given that that the valve is rigid, in the sense that there is no flexibility in the valve. All the flexibility that you have is in the spring here. So, at this end there is another spring which is fixed to the cylinder head, and this spring is having the spring stiffness let us say Ks, as you see here. The spring also has its own mass. So, in this case there is a mass of the spring as well. There is a mass of the push rod, and then there is a stiffness of the push rod. So, now you can see that it is a very simple simplified model of this apparently a more involved kind of a vibratory system, a push rod, rocker arm and valve all connected to each other. One of the simplified model is now this. So, it is like this spring is attached to the end of this rocker arm, this spring is attached to this end of the rocker arm, and the only degree of freedom now we can consider is the rocking motion, the angular oscillation theta. There is no other degree of freedom here, as you can see. Okay. And all the motion that you are seeing here, this motion and this motion are actually related to the angle theta. So, even if we consider the motion here as y and here as x, they are connected to theta. So, based on the lengths of these rocker arms, if I call this as L1, which of course is given here, and this as length L2, the rocker has these two arm lengths L1 and L2. So, what we have done is from a physical mechanism, rocker arm mechanism here, for operating the valve of for letting the fuel in the cylinder. So, there is a cylinder over here, and through the opening of the valve the fuel is let in, and that opening of the valve is governed by the camshaft's operation. So, this entire physical system is now converted into a simplified vibratory model, which is an oscillating rocker arm here, fulcrumed here with a spring attached at one end and another spring here at the other end, and the only degree of freedom we are accounting for is theta. Now, what is asked is not only getting the governing equation or solving for natural frequency, but it is almost like a design exercise. The design in the sense, although the spring stiffness is given here, what we have to see that if the spring stiffness is considered as 10 Newton per millimeter, then is there a 20% separation margin for the engine idling speed. Now, since we have accounted for only 1 degree of freedom here, it will give us one natural frequency omega n for this vibratory system. Separation margin means we already know that when you plot the response versus the operating or excitation frequency, we get a resonance like this. Okay, this frequency is the excitation frequency, and what it is asking us to check whether with this spring stiffness, either you find out which is the required spring stiffness, or if the spring stiffness is considered, whether we shall be at least 20% away from the natural frequency or resonance, right. So, whether using this spring stiffness, are we going to lie either in this region or in this region to avoid closeness to the resonance region. That is what the separation margin is all about. So, this gap should be 20%, or the frequency difference between the natural frequency and the excitation frequency should be 20% of the natural frequency. Now, how does it relates to engine idling speed? Because if we are idling at a particular speed, let us say 550 rpm, which is given here, which means that let us say I am operating at this particular position, which is 550 rpm, and the natural frequency may be somewhere here. I will have 20% difference in the two speeds, and then I will be safer. Okay. So, the natural frequency that I get by using this value of the spring stiffness should be 20% away from the excitation frequency 550 rpm. However, there is a catch here. It is the engine idling speed, it is not the camshaft operating speed, which actually means that if I operate at 550 rpm, the camshaft operates at 220. Yeah, so what? How much will it be? 225. Sorry, 275 rpm. Okay. So, the camshaft will operate at 275 rpm, and therefore, this speed will have to be accounted for as 275 rpm to account for the fact that camshaft operates at half the crankshaft or engine speed. So, using this case, what you will have to do is, first, once you get the governing equation and get the natural frequency expression, you will substitute all these values and check whether the natural frequency for this system turns out to be either 20% away from this 275, either on this side or on this side. This side is preferred for a simple reason, that this is the lowest speed with which the engine will operate. Otherwise, as you raise your engine speed, the speed is going to be increasing from 550 rpm onwards at a higher speed. So, if you can ensure that it is on this side of the 275, it will be safe for all the other higher speeds of the engine crankshaft. Alright, so with this background, let us at least get the governing equation and expression for natural frequency. Then of course, one can substitute all these numerical values in the expression to get the frequency value. Now, if we want to do that, we will have to get the expressions for the kinetic energy, potential energy, the way we found in the previous cases. So, if this is modeled like a rocker fulcrumed here, okay, and there is a spring which is that of the push rod, there is another spring here which is this particular spring, and then of course, I am considering theta as the degree of freedom. Okay. Now, what is the process for getting the governing equation? Free body diagram has been obtained. This length is L1, okay. This length is L2 as we discussed, and the mass moment of inertia of this rocker arm is J. This is the spring of the push rod. It also has the mass. So, MP is the mass of the push rod, spring, and the mass of the spring, and then of course, there is a mass of the valve here. So, mass of this valve, okay. Either you consider it here or you can as well consider it here, but then please make a note that the spring is around that valve. So, it is not in series with the valve, okay. It is parallel to the valve. So, the valve can operate up and down with the same velocity as the tip or the end of this particular rocker arm. Okay. Now, let us consider the expression for the potential energy. How is potential energy, total potential energy of the system to be obtained? All the energy that is stored in the spring elements. Now, the springs are two here, one is the push rod. So, although you do not see geometrically there is no spring as such, but this thin push rod itself acts like a spring, and the spring stiffness is Kp. So, half Kp into so if this displacement is assumed as y of t and this as x of t. Okay, so you can consider this y of t and x of t as the two displacements at the tip of this of the rocker arm, then half kp into y square. Okay. This is the strain energy that will get stored in this spring. Okay. So, you add to that the strain energy stored in this particular spring, the rocker arm being rigid. So, half of Ks into x square. Okay. X is the instantaneous deflection in the spring. Now, you can see that this x can be written as L2 into theta and y can be written as L1 into theta, is not it. So, although you show these two displacements as two different ones, but they are not, actually they are geometrically related to the assumed degree of freedom, that is theta of the rocker. All right, we will do that later, but maybe I can write this as Kp into L1 theta square plus half Ks L2 theta square. So, maybe that is the revised expression of the potential energy. What about the kinetic energy, capital T, in the system? We already have seen that there is a mass of the push rod that is assumed, right. So, if the push rod mass is to be accounted for, okay, but that mass is distributed, okay, it is not a lumped mass as such. Okay. There is a difference between the mass which is distributed of the rocker and that of the push rod. The push rod is getting compressed and it is moving. Each of these elements move with a different displacement as compared to this end of the push rod. So, each element of the push rod moves with different velocities, right. So, therefore, this is almost like a spring and we have discussed enough in terms of considering the mass of the spring. So, if that is the case, then the kinetic energy contribution from the push rod is going to be half mp into y dot square, but the mass of the push rod is reduced by reduced by to 1/3 of its total mass. That is the effective contribution of the push rod, okay, to the kinetic energy. We have seen that if the spring and mass is there, if mass of the springs is to be accounted for, its contribution to the kinetic energy will be 1/3 of its mass. Okay. Now, what else you have next in the line? The rocker arm. So, that is a rigid rocker arm and therefore, the kinetic energy of the rocker arm is j theta dot square, that is the kinetic energy of the rocker arm. Followed by, what do you have here at the other end of the rocker arm? On the right hand side you have a valve which is getting pushed, okay. That valve is not getting compressed, so it is assumed rigid. So, the mass of this valve, the cyan colored valve rod that you are observing here, that will contribute without any change, right. So, mass of the valve times what? X dot square. So, the velocity of the valve at the tip here and at this point are identical, okay, does not deflect. So, the value of the velocity is the same. So, half of mv into x dot square is the kinetic energy of the valve. But you also have the mass of this spring to be accounted for. The spring not only contributes to the potential energy term, strain energy, but also contributes to the kinetic energy. So, I will add here the contribution from the mass of the spring, valve spring here, by taking 1/3 of its mass, and then you have x dot square here. Is there anything that we missed? So, all parts are accounted for. You have push rod accounted for, you have a rocker arm accounted for, you have a spring accounted for, and you have valve accounted for. Out of these, the rocker arm and valve are already declared as rigid. So, therefore, they did not contribute into the the potential energy expression, but we looked at the flexibility in the push rod and the spring in figuring out that their own masses will contribute to the kinetic energy, but not in full. Okay, 1/3 of their masses will contribute. Now, once we have obtained these two expressions, one for the strain energy, the other one for the kinetic energy, the next step is absolutely straightforward and very simple. And so, this is the expression that we already got, the total kinetic energy, potential energy obtained. And now, what you can do is, because it should not confuse that x and y are the 2 degrees of freedom, they are not. The only degree of freedom here is theta. X and y are related to theta through the lengths of the arms, and therefore, if you substitute y and x into these two equations and then apply the conservation of energy, that is the time derivative of total energy is 0, you will find the expression for the governing equation. Okay. And the expression which I have highlighted here is obtained like what you see here, right. So, Kp, Ks, the push rod stiffness and the spring stiffness appears in the numerator, and the mass of the push rod, that of the spring, that of the valve, and of the rocker arm inertia, they all appear in the denominator as we expected. So, that is how the natural frequency expression has been obtained. So, if you really look at the overall vibration analysis process, we first looked at this physical system, considered all the possible motion, and we figured out that only degree of freedom here is theta, and then accordingly we got the a simplified vibratory model. We used energy method in this case instead of Newton's approach or application of Newton's law to get the governing equation of motion and get the natural frequency expression from that. Once you do that, we have to do inferencing, right. That is what we said. Once you get to solve for natural frequency or vibratory response, how do we make sense out of this outcome, right. So, I would suggest that you use the numerical values which are given in the previous slide to obtain the value of omega n, and then what has been asked or what has been indicated in the example is that either you find the value of the spring stiffness here Ks, so that this resonance is kept 20% away from the engine idling speed. Now, we have seen that if the engine operates at 550 rpm at its idling condition, the camshaft will operate at 275 rpm, and it is the camshaft that is pushing this entire vibratory structure or exciting this vibratory system. So, for me the excitation frequency omega is going to be 275 rpm. Now, this of course will give you in radians per second, you will convert that into rpm, and this omega n, whatever you get by substituting all the numerical values, will be this value. And what you are supposed to check is that whether this gap between the natural frequency of this vibratory system and the excitation frequency for this vibratory system is whether those frequencies are away by 20%. It is preferable that the natural frequency lies on the left of this rather than figuring out that your 275 rpm is here and the natural frequency is on the right side. Why? Because as the engine picks up its speed, it will anyway then again cross through that resonance region. So, it makes more sense to consider the spring to have a stiffness in such a way that the natural frequency lies on the left side of it. That is how the outcome of these natural frequency expression and the values should be interpreted or should be considered in the vibration based design of the mechanical system. Okay. Can we solve this same expression and governing equation using the Lagrangian equation? Yes, I think that is left to you as an exercise. Let me remind you that the expression, the Lagrange's equation is given by this. So, if I want to apply this to the existing example, the time derivative of dou t over dou x I is nothing going to be dou t over dou theta dot. Okay, so, you will have to first take the time derivative of this kinetic energy with respect to theta dot, derivative with respect to theta dot minus dou t over dou theta, because our generalized coordinate is theta, and then plus dou v by dou theta equal to 0. Can we do that? Now, if we suppose try to get apply this Lagrange's method, let's find out what the expression gives us if we apply that. So, if we take this derivative, I'll write this as dou t of dou t over dou theta dot. Now, the expression for t is here with respect to theta dot. If I take the time, if the derivative of this is obtained with respect to theta dot, then I get what? Half mp over 3 and then L1 square 2 theta dot. Okay, that is what you will get. If you take the derivative with respect to theta dot, it will not turn to theta double dot here. And then what? Plus half 2 j theta dot plus half mv L2 square 2 theta dot plus half ms over 3 L2 square 2 theta dot. That is what you will get as this particular term in the Lagrange's equation. And the second term says that dou t over dou theta. Now, please make a note that this expression does not have any theta in its in its terms. So, this value is going to be 0 for this case, and plus dou v by dou theta, which means that you find out what is the derivative of this with respect to theta, and then of course, I can get this as half k p L1 square 2 theta, okay, and plus half k s L1 square 2 theta equal to 0. And now, if I take the time derivative of this expression, then what? Then I get mp by 3 L1 square plus theta dot will change to theta double dot plus j theta double dot, right, plus mv L2 square theta double dot plus ms over 3 L2 square theta double dot plus kp L1 square theta plus ks L1 square. I think this should be L2, this is a printing mistake here. So because x is L2 into theta, so pardon me for this small change here. This has to be Ks into L2 and not L1. So that gives us Ks into L2 square into theta equal to 0. That is what the equation that we finally get. But if we bring in all the terms in theta double dot together, then I have j plus mp over 3 plus ms over 3, oh sorry, mp into L1 square, and then this becomes ms into L2 square and plus mv into L2 square theta double dot plus kp L1 square plus ks L2 square into theta equal to 0, which is in a standard form of mx double dot plus kx equal to 0, which gives us the expression for the natural frequency as kp L1 square plus ks L2 square over j plus mp over 3 L1 square plus ms over 3 L2 square plus mv L2 square. Okay, that is the expression I have. You expect the same expression, and that is, I guess, is what we are getting here. So, to summarize this lecture, we had a good introduction to the energy based method as an alternate to the Newton's of law based method of getting the governing equations of motion. And within the energy methods, we explored several alternatives. The ones which are used more are the conservation of energy, where we take the derivative of the total energy to be equal to 0. With that, we can get the governing equation of motion. Alternatively, Lagrange's equation, as I mentioned, is a more classical way of getting the governing equation of motion, and hence for a simple case an expression for the natural frequency. We discussed a couple of examples and saw that if we include the mass of the spring in getting the expression for the total energy, the spring mass can contribute to the natural frequency. Okay, these are the questions related to today's lecture, and a very simple question on the energy method. So you may now have a go at these questions, try it out yourself, and then verify your answers with the answers given in the next slide.